Bam, Mr. Taru. We are going to, in this video and the next, discuss how to solve systems of nonlinear equations into variables. Basically, we're going to be finding out where things like a parabola and a circle cross, or a hyperbola and a straight line. We're going to be doing two videos, one for substitution method and one for linear combination, or the addition method. And it's quite difficult to find examples or to come up with examples of this type of problem that work out fairly neatly. So I hope my examples are good and they help you understand what's in your textbook. So, step number one, solve one equation for one variable. Step two, substitute that expression into the other equation. Step three, solve for remaining variable. Step four, back substitute your answer into one of the original equations. And very, very important here, especially since we're dealing with powers of 2. So we'll be squaring both sides of equations and we're square rooting. It's very easy to get some extraneous answers. An answer that, comes out from the algebra but will not actually be a solution. When you plug it back into your original problems, it will not check out. So please make sure to actually check your answers. This is not just sort of like a teacher saying you should always check your answers. Like, you really should be checking your answers to make sure you got all your solutions that actually work and you don't have any extra solutions that do not work for the original problems. These steps sound very familiar. They're just like solving a two-variable linear system, but the fact that we have nonlinear systems and we'll have powers of 2 or quadratics in our equations can lead to some rather difficult settings and even some problems that you would not really want to solve by hand but allow your graphing calculators to help you. So let's get this board cleared out and get our first example. Never mind. I just realized how much work I had left to show and I got room. So I thought maybe it'd be nice if I kept all this up here for you at once. We're going to take this equation, which came from just a small manipulation of the second equation. I just basically subtracted by 4x and divided by -1. So I'm going to take this equation and bring it over here. So I got y equals 4x plus 4. And let's plug in this equation, this part here, x. So we have x is 5/2. So we got y is equal to 4 times 5/2 plus 4. Now, 4 divided by 2 is equal to 2. So where the fractions go away quite quickly. 4 divided by 2 is 2, and 2 divided by 5 is equal to 10, plus 4, or 14. So one possible intersection point is 5/2, 14. The second point is going to come from our x value of -1/2. So again, into this equation of the line where the line is intersecting the parabola, we got y is equal to 4 times -1/2 again. Well, not again, the first time, excuse me. Plus 4. 4 divided by -2, or 4 times the -1/2 is -2, plus 4 is equal to 2. So my other point is x is -1/2, so -1/2, 2. Okay, now I told you it's very, very important for you to check your work and make sure that your solution works for not one of your equations, but both. So this x and y value must make both the first equation true. So 4 times 5/2 squared minus 2 times y, which is 14. We need to make sure that that's equal to -3. We've got to make sure that 4 times, again, 5/2 for x minus the y value of 14 is equal to -4. And then also check your second point. So again, 4 times -1/2 squared minus 2 times that y value is 2 equals -3. And 4 times -1/2 minus 2 equals -4. And make sure that works as well. And that is the end of our first example. Let's get the second one done just to make sure you really have it nailed down before I move on to the addition method. Second example. We again have a linear equation for our second equation, And our first equation has both the x squared and a y squared term. They're both positive and they both have the same coefficients on the x squared and y squared. So when you get to the section in your book where you're studying conic sections, you'll understand that this is the general form of a circle. So we're going to find out where a straight line intersects a circle. Okay, so we're going to take this second equation, which is clearly the much simpler of the two, solve it for a variable, and substitute it into the other equation. This problem would be a horrible candidate for attempting to do the addition method. This pretty much can only be done with substitution, at least as far as being, at any reasonable easiness. So I'm sure somebody can come up with some way that the addition method would work, but we're going to stick with substitution. If I try and solve for y, I'll make fractions I have to carry through the rest of the problem, so I'm going to solve or find this equation, or set this equation equal to x. So we're going to subtract both sides by 3y and get negative x equals negative 3y plus 5. We're going to divide everything by negative 1 and get x is equal to 3y minus 5. And now we're going to take this expression and substitute it into the first equation anywhere that we happen to see an x. So there we go, right off the bat. X squared, so we're going to do parentheses x, which is 3y minus 5 squared plus y squared plus 3x minus 9y plus 10 equals 0. We're going to have to distribute this binomial together, so that's going to be, well, 3y minus 5 times 3y minus 5. We're going to distribute that all together. Add like terms. Make sure you do this, please, so that you catch that there's three terms, that middle term is there. A lot of students will just write 9y squared minus 25, which is incorrect. And you'll see your trinomial. This is going to be 9y squared. 3 and negative 5 is negative 15. So negative 30y and then plus 25. Plus y squared. 3 times 3 is 9. And 3 times negative 5 is negative 15. Minus 9y plus 10 equals 0. Okay, add like terms. We have 9 and 1, which is 10y squared. Let's see, we have 30y, we've got positive 9y and negative 9y, so those are going to cancel out. So we just have minus 30y, and our constants are 25 minus 15. So 25, 20, 10, plus 10 is 20, which is equal to 0. Now we have a quadratic, we have a leading coefficient that's very, very big, but I can just divide both sides of this equation by 10, and that's going to reduce a lot of this. 10 divided by 10 is 1, so y squared. 30 divided by 10 is negative 3, because it's negative. I forgot to say that. 20 divided by 10 is 2, and 0 divided by 10 is 0. Now we got a nice, easy, small quadratic. We have a leading coefficient of 1 that doesn't make this too hard to factor, unlike the last example. So factors of the first term go in the first two blanks, and there's not much there since it's just 1y squared. Factors of the last term go in the last two blanks. The last sign's positive, my middle sign is negative, so they both need to be negative. Factors of 2 that add to 3, not much choice since 2 is prime. We got y minus 1 times y minus 2 equals 0. Set each one of these equal to 0. And we get y equals 1 and y equals 2. Okay, we're ready to back substitute and find our two intersection points. So, let's take again our slightly modified second equation and get x is equal to 3 times y. First y is 1. minus 5. So x is equal to 3 minus 5, which is x equals negative 2. So our first point is negative 2, 1. And our next point, y equals 2, is x equals 3 times the y value of 2 minus 5. That's 6 minus 5. That is x equals 1. And our last intersection coordinate is 1, comma, what did I use again? 2 to get that. Now, don't forget, take those coordinates, plug them back into both of the original polynomials, original equations, to make sure that they actually work. I've already done that, so I'm not going to do it again. I'm Mr. True. Bam! Go do your homework. Or watch my next video of how to do this with the addition method.